Hello, welcome to section 8.3, Trigonometric Integrals. We just looked at integration by parts, and now we're going to be shifting gears and looking at a different type of integral. So the goal of this section is to be able to integrate integrals of the form integral of sine to the m of x cosine to the n of x dx for m and n positive integers. So we're looking at powers of sine and cosine. So a little bit of motivation for how we're going to be doing these. Evaluate the integral of cosine to the fourth of x sine x dx. So I'm going to let you guys try this, pause it, see if you can integrate this function. You have all the tools to integrate this particular function. All right, so we look at it when you see it's the product of two functions. So you think, oh, integration by parts, because that's fresh in your head. You don't want to use integration by parts because what would you let u equal? According to Liotti, it could be either of them, and neither of them terminate. So then you look at it a bit closer, and you realize that you can do the U-Substitution, let u equal cosine x. So du would equal negative sine x dx. So then this integral would be negative integral u to the fourth du, which is negative u to the fifth over 5 plus c, which is negative cosine to the fifth x over 5 plus c. So already we can integrate some of integrals of the trigonometric form, powers of sine and cosine. But really, what did we do here? If you have m or n, everything I'm going to say about m you can also do with n, equal to 1. Then you can do a simple U-Substitution. To solve these integrals. So the goal for these trigonometric integrals is always going to be to get either m or n equal to 1 using trig identities. Right, so for the first type that we're going to look at, we're going to use all the same type of identity. So recall the biggest identity in trig, and that is sine squared x plus cosine squared x equals 1. So if you were to solve these for sine or cosine, you get cosine squared x equals 1 minus sine squared x, and sine squared x equals 1 minus cosine squared x. Boxing it in blue means you should know this, but I wrote it in black text because you should already have known this. So these will be the identities that we're going to use for the first type of integrals. So let's see how we can use them. Example. Let's evaluate integral of sine cubed x dx. So right away we see we can't just do a simple U-Substitution. because in this case we don't have m or n equal to 1. So our goal is to reduce the 3 down to a 1. So we use sine squared x equals 1 minus cosine squared x. After doing this, we'll have sine x times 1 minus cosine squared x, which we're about to see. So we would have reduced the 3 in the exponent of sine down to a 1 by changing 2 of them into cosine. So the integral of sine cubed x dx equals the integral of sine squared x times sine x dx, which is the integral of 1 minus cosine squared x times sine x dx. Now that we have m or n equal to 1, we're going to do a U-substitution similar to what we did up top. So let u equal cosine x, let u equal the thing that isn't the power of 1, and du would equal negative sine x dx. So our integral becomes negative integral of 1 minus u squared du, which we can throw that negative sign in, and that's 1 minus, no, I didn't actually throw it in. That would be u squared minus 1 du. Integrate this, you have u cubed over 3 minus u plus c, which is cosine cubed x over 3 minus cosine x plus c. So this is how we're going to be using our trig identities, sine squared equals 1 minus cosine squared x, and the analogous one, cosine squared equals 1 minus sine squared x. You're going to use them to reduce one of the m or n down to just 1. So let's do another example. Evaluate integral of sine to the 5th x cosine squared x dx. So looking at this and looking at the previous example we saw that using the identity once reduces a 3 down to a 1. In other words, you're going to be subtracting 2 off the exponent every single time you use the identity. So we cannot use the identity on cosine squared x and expect to be able to integrate this function because then you'll have cosine to the 0, not cosine to the first. So you need m or n equal to 1, not 0. So we know that we have to use the same identity to reduce the 5 down to a 1 instead of the 2. So since we lower m or n by 2 every time we use the identity, we must manipulate sine to the 5th x. Okay, so let's do that. The integral of sine to the 5th x cosine squared x dx equals, we're going to pull out as many sine squareds as possible. So that is sine squared x squared times sine x times cosine squared x dx. Apply the trig identity on the sine squared x. So that is the integral of 1 minus cosine squared x squared times sine x cosine squared x dx. And then now that we have 1 power of sine, we let u equal cosine. Then du will equal negative sine x. So our integral becomes the integral of 1 minus u squared squared. The sine x is absorbed in the du. And I forgot my negative sign, so let's put that out there. And then we have cosine squared, which is u squared du. Okay, go ahead and expand this. We have negative integral of 1 minus 2u squared plus u to the 4th times u squared du. And then distribute the negative sign and distribute the u squared. And we have the integral of 2u to the 4th minus u to the 6th minus u squared du, which is 2u to the 5th over 5 minus u to the 7th over 7 minus u cubed over 3 plus c. Finish the problem by undoing the substitution. 2 cosine to the 5th x over 5 minus cosine to the 7th x over 7 minus cosine cubed x over 3 plus c. So all the examples we've seen so far, we have let u equal cosine x because we have been manipulating sine. So let's do another example and see that you can do the same thing by manipulating cosine and let u equal sine. So evaluate. And by evaluate, this one gets a little bit messy, so we will just set up the substitution. So evaluate or set up the substitution for the integral of sine to the 7th x cosine to the 5th x dx. Okay, so with this one, first off, we see we have 7 and 5. They're both odd, so we could manipulate either of them. But, like I said, we're going to manipulate cosine so that we see we can manipulate either of them. So we will use cosine squared x equals 1 minus sine squared x. So the integral of sine to the 7th x cosine to the 5th x dx equals the integral of sine to the 7th x. Pull out as many cosine squared as possible, so you get cosine squared x squared times cosine x dx. Use the trig identity, so we have sine to the 7th x times 1 minus sine squared x squared times cosine x dx. And then now that we have only one power of cosine, we want that to be absorbed into the dx. So we're going to let u equal sine x. So we have u to the 7th times 1 minus u squared squared du, which is good enough. I said just set it up. And this isn't that hard to integrate. It's just going to be the same thing. Expand this and then distribute the u to the 7th. But if you were to manipulate the sine to the 7th x and then let u equal cosine x again, you'd end up with the integral negative quantity 1 minus u squared cubed times u to the 5th. And that's a lot harder to expand because, I mean, you have a cubed. I don't want to expand that personally. So while you can use either, you can manipulate either side if they are both odd, there is a right choice, or not a right choice. There is an easier choice. And it's generally going to be whichever one has the lower exponent. You should manipulate whichever has the lower exponent. So in general, let's just summarize what we have so far. So for the integral sine to the mx, cosine to the nx dx, if m is odd, we will use sine squared x equals 1 minus cosine squared x, and the substitution u equals cosine x. If n is odd, then we will use cosine squared x equals 1 minus sine squared x, and the substitution u equals sine x. And then if m and n are odd, then manipulate either, comma, preferably, sure, that looks right. That does not look right. It's good enough. That is preferably. Preferably whichever is smaller. Okay, so example. I haven't had you do anything yet. So evaluate the integral of cosine cubed x sine squared x dx. Why don't you pause it, try it, and then unpause it when you're done and make sure that you agree with what I did. Okay. So here we have n odd. So we use cosine squared x equals 1 minus sine squared x, and u equals sine x. So then du would equal cosine x dx. So we have the integral of cosine cubed x sine squared x dx equals the integral of 1 minus sine squared x times cosine x times sine squared x dx. And then doing the u substitution, we have the integral of 1 minus u squared times u squared du, which is the integral of u squared minus u to the 4th du, which is u cubed over 3 minus u to the 5th over 5 plus c. And then undoing the substitution, that is sine cubed x over 3 minus sine to the 5th x over 5 plus c. Not too bad so far. So we have seen what happens if at least one of m or n are odd. But now the question arises of what if neither m nor n is odd? If that's the case, we use the identities sine squared x equals 1 minus cosine of 2x over 2, and cosine squared x equals 1 plus cosine 2x over 2. Boxed in blue means you should know it. So let's see this in action. Example. Now let's just evaluate something simple. Integral of sine squared x dx. Okay, integral of sine squared x dx. This is using the above identity, the integral of 1 minus cosine of 2x over 2 dx. which is 1/2 integral of 1 minus cosine 2x dx, which is 1/2 times x minus sine 2x over 2 plus c. So notice what I did here. So integrating 1, I think we're all good with that. Integrating cosine of 2x, you do let u equal 2x, then du equals 2 du. 2 dx. So then dx would equal du over 2, which is where that over 2 comes from. We will be doing this enough times that skipping this U-substitution is perfectly fine, as long as you get it right. And sometimes you'll have to use all these identities multiple times, which will just take, can lead to some long problems. So let's do a long problem. Example, we will evaluate the integral of sine to the 4th x times cosine squared x dx. Okay, so when they're both even, notice that the goal before was to get one of them down to 1, and you could technically use the cosine squared x equals 1 plus cosine 2x over 2, and then you only have 1 power of cosine, but you then can't do your U-substitution that you want because you have something different inside of the cosine. So when both of m and n are even, you're going to use both trig identities to just completely convert everything into cosine 2x. So the integral of sine to the 4th x times cosine squared x dx is the integral of 1 minus cosine 2x over 2 quantity squared, because sine to the 4th is sine squared squared, and everything in the parentheses is sine squared, times 1 plus cosine 2x over 2 dx. This is 1/8, pulling out the denominators, integral of 1 minus cosine 2x times 1 minus cosine 2x times 1 plus cosine 2x dx. Which is 1/8 integral of 1 minus cosine 2x. And then here we have a difference of squares, or a special product that will be a difference of squares. 1 minus cosine squared 2x dx. Okay, that's 1/8 integral of 1 minus cosine 2x minus cosine squared 2x plus cosine cubed 2x dx. Okay, now we need to integrate this. So 1 minus cosine 2x. I'm just going to say that's easy. Integral of 1x, integral of cosine 2x, that's going to let u equal 2x, and then simple substitution. The cosine squared x and the cosine cubed x, we're going to have to use tactics from this section. Okay, so that's 1/8 times integral of 1 is x. Integral of negative cosine of 2x is negative sine 2x over 2. We then have minus 1/8 integral of cosine squared 2x dx plus 1/8 integral cosine cubed 2x dx. So just expand this integral. Okay, and I'm going to move all the way over here to give myself space. So we have x over 8 minus sine 2x over 16 minus 1/8 integral. This integral right here, we have an even power of cosine. So we're going to use the above identities, 1 plus cosine of 2x. However, our cosine squared already had a 2x, so we're really doing 2 times 2x. So another 4x over 2 dx plus 1/8 integral. Here we have an odd power of cosine, so we're going to do the trig identity cosine squared equals 1 minus sine squared. So we have 1 minus sine squared of 2x times cosine 2x and then dx. And then for this integral, we let u equal sine of 2x. So du will be 2 cosine 2x dx. And then the middle integral, we will let u equal 4x. So du will equal 4 dx. Okay, so we have x over 8 minus sine of 2x over 16 minus 1/8, actually 1/16, let's bring that 1/2 out. Integral of 1 is just x. Integral of cosine of 4x will be plus sine of 4x over 4 plus we have 1/8 from outside the integral. Doing the du will give us another 1/2. So we have 1/16 integral 1 minus u squared du. So this is x over 8 minus sine of 2x over 16 minus x over 16 minus sine of 4x over 16 times 4 is 64 plus x over 16 from integrating the 1 minus u cubed over 48 plus c. And I made a boo-boo. We do not have x here. Oh, that's not an eraser. We don't have x here, we have u here. So recall what u was. U was sine of 2x. Let's go ahead and plug that in. We have x over 8 minus x over 16. That is just positive x over 16. We're going to have minus sine of 2x over 16 minus sine of 4x over 64 plus sine of 2x over 16 minus sine cubed of 2x over 48 plus c. And then we're basically done. We can just see that we can eliminate the negative sine of 2x over 16 and the positive sine of 2x over 16, leaving us with x over 16 minus sine of 4x over 64 minus sine cubed of 2x over 48 plus c. So really the takeaway from this example is that if you have both m and n even, then you have to just you convert all of them to cosine of 2x. And then it gets messy because if you do that, you're probably going to have to use more techniques from this section again. And as you can see, it gets pretty long. So last comment is that we can use similar techniques for integrals, the integral of tangent to the mx secant to the nx dx. Using the identities, we have tangent squared x equals secant squared x minus 1, and secant squared x equals tangent squared x plus 1. So, quick example of this. Evaluate the integral of tangent squared x secant to the 4th x dx. So the first thing we note when doing this is what substitution are we going to want to make? So if we let u equal tangent x, then differentiate this, you get du equals secant squared x dx. So we want n to equal 2 after applying, or let's not say applying, let's say using the trig identities. Luckily we can do that because secant to the 4th, we have an even power for n. So we'll just use secant squared equals 1 plus tangent squared x, and then we'll have the secant squared left over that we want. So the integral of tangent squared x secant to the 4th x dx equals the integral of tangent squared x times tangent squared x plus 1 times secant squared x dx. We then let u equal tangent of x, so du equals secant squared x dx. And our integral becomes u squared times u squared plus 1 du, because the secant squared is absorbed into the dx. That's the integral of u to the 4th plus u squared du, which is u to the 5th over 5 plus u cubed over 3 plus c, which is tangent to the 5th x over 5 plus tangent cubed x over 3 plus c. So similar method as to sine and cosine. We just have a different target because the derivative of what we're going to want our u to be, so tangent, is different. And the same thing will apply if you wanted to let u equal secant. So if you recall, let's get blue, if u equals secant x, then du equals secant x tangent x dx. So our goal would be to get rid of all but 1 power of tangent x if we wanted to let u equal secant x. And then that's assuming we have a secant x left over. If we just have the integral of tangent squared x, you probably don't want to use the identity, because then you just have secant squared x and you can't make the proper u substitution.